Good morning. Happy Monday. Last week before spring break. Ray Reed asked a question I think all of you would benefit from knowing the answer to. No, well, we will almost finish this unit before spring break. We will not totally finish the unit before spring break, and we're losing some people early. So for their sake, it's probably good that we don't. We will finish it basically the week and a half maybe back from spring break, so you will have a test on this unit pretty close to when we get back. And Kai, you're leaving early. Before you leave for the break, I will have a chapter review available to you that you can take if you would like it. We won't be totally done the unit, but it'll be available to you. So, Kai, if you want that, take it before you go. So I assigned a bunch of velocity time graph questions on Thursday, Friday. I'll give you the answers to that, and then we'll talk about the acceleration due to gravity. So I'll provide you the answers, compare what you got with what I got. If you've got any questions you'd like me to go over, want me to explain anything, I'm happy to do that. Here are the first two. Comments, questions, concerns on the first two. Half a meter per second squared, 6 meters, 0 and 0. Comments, questions, concerns on any of those? Okay. I am recording. Good. 4 to 7 seconds, -5, 0 it turns around, and 5. Comments, questions, concerns on any of these? Going once, twice, thrice, sold. These guys slows down as it moves backward, then speeds up forward. -2, slows down forward, changes direction, speeds up backwards. -2. Questions, comments, concerns on any of these? Is there anything in there anyone would like me to go over or explain, discuss? And there was a lot of discussion I had with a bunch of you on these questions last week, so I think I've addressed most of those. Kale and Kai made me change a couple of my answers. We're good? Okay. Then the next chunk was, if I'm not mistaken, this page. The answers to that page look like this. 0, -2, 0, 2.5, and -2, all meters per second squared. 7 seconds, 90 meters per second squared. -400 meters per second squared. Increasing, decreasing, constant, and constant. Anything there anyone would like me to discuss? The car hitting the tree? Okay. So they give you, so it says a car hitting a tree loses 40 meters per second in 0.1 seconds. What is its acceleration? So a car hits the tree. After the car hits the tree, presumably the car comes to a stop. So the final velocity for the car hitting the tree is 0. The initial velocity for the car hitting the tree is 40. So you're going to have VF equals VI plus AT. They give us a time, an initial velocity, a final velocity, and we want to find the acceleration. So we're going to have 0 equals 40 plus A times 0.1. If I subtract 40, divide by 0.1, you're going to get -400. -400 meters per second squared. Massive deceleration. This is why airbags and crumply cars are a thing. Okay, on the back, your answers should have been 0.06 meters per second squared, that should be 0.06 repeating meters per second squared, 0.13 repeating meters per second squared, 0.075 meters per second squared, and 0.0694 repeating meters per second squared. Is there anything there anyone would like me to go over? Comments, questions, concerns? On this one? Previous page? Okay, which one? Okay. So you're just finding slopes for each of these? A and C, the slope is 0. Each one of these letters represents just a chunk of the line. So A is that chunk, B is this whole diagonal piece, C is that piece, D is this whole diagonal piece, E is this whole diagonal piece. And you're just finding slopes. Just rise over run for each one of those. So like for example, B would be a drop of 1, 2, 3, 4, 5, 6, and a run of 1, 2, 3. So if you're dropping 6, that's going to be -6 over 3 is -2. You go from 7 down to 1. Does that make sense, Brad? Did anyone have any discussions about this one? Questions, comments, concerns? It just goes back to the definition of acceleration. Change in velocity over change in time. Velocities you read right off the graph. Times you read right off the, well, time intervals they give you. Okay. And then I think I wanted you to skip this. You can leave it to the review. If anyone did them, I do have a key for this. I can show it to you later. But I wanted you to, I changed what I assigned. Skip that, skip that. I wanted you to attempt this instead. If you did attempt it, great. If you didn't, I'll give you the answers for it. Your answers should look like this for each of these questions. 312.5. You can, if you didn't do these, by all means, write down these answers, so that should you go back and get these things done, you can verify that what I've got is correct. If you did do them and you got something different, let me know. But 312.5, 500, 5.5 meters, 67.5 meters. That's the distance which Vera would travel prior to completing the stop, assuming she did not collide at the pickup. So yeah, she hits the pile up. 487.5 meters. And question 6 is 8 seconds. The time for Luke to drop back to the original height of the cliff is 8 seconds. Is there any of these questions anyone would like me to demonstrate? For each one of these, you were solving them using velocity time graphs, and then for 6, I wanted you to draw a displacement time graph from the velocity time graph. Comments, questions, concerns? Going once, twice, thrice. Okay, you guys are so quiet. Okay. So then, you know what you did, you know what you didn't do. Jump to this. We're going to look at a very specific kind of acceleration today. Oh, where do I want to be? I want to be that one. Which one do I want to be? Not that one. I want to be this guy. Here we go. Okay, so we talked about accelerations. We looked at some of these kinematic equations. We're looking at a very specific kind of acceleration that all of you have experienced, I would think, over the course of your life, and that is the acceleration due to gravity. What happens when you toss a ball in the air? It goes up. And then what, Brad?
After a while, it goes back down again.
After a while, it goes back down again. Balls. We can demonstrate. For those of you who have never thrown a ball up into the air, should not hit the lights. It goes up, it comes back down. Why? Gravity. Okay, cool. We all have a functional understanding of gravity. So if I take my baseball, I throw it up in the air, comes back down, doesn't change depending on the kind of ball I have. Whether it's a golf ball, a tennis ball, a baseball, they all behave basically the same way. Assuming I'm throwing them up, the same initial velocity, they all seem to go up and come back down. Interesting. And we're blaming gravity for this. We have Isaac Newton to thank for that. You guys have all seen the classic example. He sits under the tree and then the apple falls hits him in the head. You're like, oh, gravity's a thing. Doesn't quite happen that way. So let's break down what Brad said in way more detail than perhaps you ever thought was necessary. So we have a ball. The ball being thrown upward means that the ball has some sort of initial velocity. So there's some VI. And because this thing's working in a couple different directions, well, two different directions, it goes up, then it comes back down, we have to specify which way we want to consider positive to be. So which way, Brad, do you want to be positive?
If we're throwing it up, then the VI going positive.
Okay, so you want to call that initial velocity positive. Okay, cool, we can do that. So the thing goes up, and then you said the thing comes back down. If it goes up and then comes back down, you say gravity is acting on the thing. Which way does gravity have to be acting? Which way does gravity act? It pulls things down. So the acceleration due to gravity is downwards. The acceleration, because it's, gravity is pretty universal. It's going to be downwards the whole time. And it's going to be constant. So we're going to have some negative acceleration. Brad called up positive earlier. There'll be some negative acceleration downwards. So as soon as the ball leaves my hand, what's it doing? It's going up and? As soon as it leaves my hand, am I accelerating it anymore? Okay, so how you break this down in your brains really, again, we're breaking this down into way more detail than you ever thought was probably necessary. I'm going to use the tennis ball because it's not going to hurt quite so much if I hit someone with it. As soon as, so I'm going to throw it. As soon as it leaves my hand, am I accelerating it anymore? No. So then what takes over accelerating this thing? Gravity. So as soon as the thing leaves my hand, it starts accelerating which way?
Up, positive.
Down. As soon as it leaves my hand, it starts to accelerate down. So my hand gives it the initial velocity, and it immediately starts to slow down. It's going to reach some maximum. At that max, it's going to turn around. So at the peak, the velocity is 0 for an instant. Really important detail that we take advantage of all the time. So there's going to be some maximum point that the thing reaches. Because there's a maximum point, this is where it turns around at the turnaround point for a literal instant, the smallest amount of time you could possibly measure. Velocity is 0. And then the thing starts to accelerate. It continues to accelerate downwards, but now the velocity is also downwards, so it's speeding back up towards my hand. There's one more interesting detail here. If it's constant acceleration, oh, dang it, so close. If the acceleration is constant, what can you say with the velocity it goes up versus the velocity it comes back to my hand? Assuming I throw it and catch it at the same height.
Does it come back down faster because gravity is pulling it down?
That's a good question. That's what I'm asking you. Does it? If I throw it from this level, it leaves my hand at some velocity. It's accelerating at the same rate the entire time. Then it comes back and lands back in my hand at the same height I threw it from. Does it make sense that it would be going faster coming down than it was going up? You're just throwing something out. You think it's the same. Why do you think it's the same? Intuitively, you're like, it should be the same. Like, it's the same distance up, it's the same distance down. It left my hand with some velocity. It doesn't, nothing's boosting it. It doesn't make sense that, like, here doesn't get a rocket motor throwing it upwards. It goes up, it comes back down to the same height. It would make sense to some of us intuitively that the final velocity is equal to the initial velocity, just the opposite direction. And if that's not intuitive to you, that's okay. We can prove it mathematically, but Kai, you're right. When an object, when you, excuse me, if the object reaches the same level, at this point here, that same ball is going to be going downwards once it reaches that level. The final velocity here is going to be negative. And when they're at the same level, these two, the magnitudes are equal. At the same level, these are equal and opposite. Okay, cool. I threw 3 objects into the air. Did they seem like they were behaving any differently? Demonstrate some stuff here, shall we? This one, pretty light. This one's pretty heavy. Okay, acceleration due to gravity. Let's drop some more stuff. Do this. One of those is more massive, would you say? Probably that one. So I've got 2 books. If I let them go at the same time, what's going to happen? The heavier one's going to hit the ground first? Yeah. Anyone disagree with that? Why though?
Gravity affects heavier things.
Gravity affects heavier things differently?
Yeah, you saw it speeds up faster. It doesn't know what surface it is.
Just drop it. Just drop it. Okay. But why? Why would it affect different things differently? Let's throw it again.
There was this thing where it was like a bowling ball and a feather dropped in like some vacuum area, right?
Yes, you've seen the video?
Yeah.
Did I show you the video? I didn't have you inside. I mean, I can kind of demonstrate. Yeah, these are 3 different balls, right? There's different masses. Yeah. Yeah, obviously different masses. Then throw a golf ball in there. Golf ball's the lightest. If I throw all 3 of these straight up. Ooh, catch it. Thank you. It looks like they kind of all behave the same way. They were all different masses according to Kai. If I drop these 2, they fall at different rates.
I feel like you need more distance.
You need more distance. Okay, so I have to go higher. Should we go to the rotunda and drop stuff off for a second? Okay, let's go to the rotunda and drop stuff off. Why not? Let's do it. I'll bring this guy. I need something heavier than this guy.
Gotta go?
Sure, let's go to the rotunda. I'm gonna bring these obviously different masses. What can I drop off the rotunda? Here, carry that guy. This is not heavy. I need something heavy. I was not expecting to go drop things off the rotunda.
I was expecting you to say yes.
I need something more massive. It's going to shatter almost certainly. I need something more massive. Okay. What can I drop off this? You know what? I'll drop the textbook. Here we go. This is a better book to drop. I actually like this one. Okay. Oh, your book's still alive. Yeah, the book's still intact. Which is pretty impressive. Pearson did a good job of putting it together. If anything you want, like you can hold these, you can see there's obviously a difference in mass. What I'm going to do it again, I'm hoping I've justified altitude and changed the thing. But I'm going to demonstrate a few more things because you were suggesting that air resistance could have been a thing. But these fell at the same rate. Let's do this. If I drop a piece of paper and the textbook at the same time, what's going to happen? Paper's going to do what? It's going to float. Why?
Because it's really light.
Because it's really light. But that one's really light compared to this, and they fell at the same rate.
But it doesn't have that much surface. The wind kind of go around it.
Okay, so you said the paper's okay.
Yeah.
So I drop these. Okay. So they fell at different rates.
Yeah.
But I did the first one first to try and convince you that mass had nothing to do with it. So it's not the mass of the paper that's the problem. You're suggesting it's the aerodynamics of the paper. So if I put the paper on top of the book, what should they do? They should fall the same rate. They do. So there's a few different, when I do these demos, there's a few different misconceptions of trying to dispel. You've seen the bowling ball video. You saw the bowling ball and the feather, and they fell. The feather does this, the bowling ball hits. And then you saw the second half of that video, where they pump all of the air out of that massive chamber, and they fall, the feather and the bowling ball get dropped, and they fall at the same rate. I'll show you that video next chapter, for those of you who have never seen it. This demo I'll do now, the other one I'll do, the video I'll show you later. So mass has nothing to do with it. Aerodynamics plays a huge part. This is less aerodynamic than this. These ones have basically the same aerodynamic profile, but they fall at different rates. So mass does seem to have something to do with at least part of it. But when I put one on top of the other, the textbook pushes all the air out of the way. The paper doesn't experience any air, and they fall together at the same rate. That's interesting. So the acceleration due to gravity. The thing I'm trying to demonstrate here is that the acceleration due to gravity, whatever that value is, impacts everything equal. The bottom of these things, or the bottom of the rotunda, when I drop both of these together, they hit the same rate. So their acceleration was the same. The acceleration due to gravity was the same for both these objects. Why? Hands up if you'd be willing to catch this in the rotunda. So Dwayne was down there, he would have caught this. How many of you would have caught this? Actually. Why? What's the difference then between these two? There's a whole bunch of misconceptions I'm trying to dispel here. I'm trying to get you an accurate mental picture of what's really going on here. What's the problem with catching this thing versus catching this thing? What do you mean?
There's a lot of inertia behind it.
And the inertia is a big part of it. Inertia is dependent on, did we talk about what their inertia is dependent on? We didn't talk about what inertia is dependent on. Julie? What do you mean? What force is different when they arrive at the bottom? So you got your book, you got the volleyball, they reached Dwayne. Traveling at the same final velocity. I'm hoping I've justified that for you. They hit the ground at the same time, means the acceleration was the same, the initial velocity was both 0, which means they're going to hit Dwayne at the same VF for that guy is going to be equal to VF for this guy. If gravity is impacting these things equally, what's the problem with catching that one versus that one? We're talking about forces. You talked about inertia. We didn't really talk about inertia. We will next chapter. But what's your understanding of inertia?
Well, it's like if you stick your hand out and the ball hits your hand, it's not really going to do anything. But if you stick your hand out and don't do anything to control the inertia that's coming at you, the ball's going to destroy your hand.
Okay, so we've got some understanding of inertia. We have not defined it at all. We just, at the beginning, we talked about that inertia was a thing. Or inertia, I think, I can't remember who. I think it might have been Lachlan. It's an object's tendency to keep whatever motion it has. You recall his definition for this a couple days ago? A week ago? Yes? No? Okay. So, who has more inertia? If I run at you versus my 4-year-old's running at you, which one of us has more inertia? What does your intuition tell you? Probably me. Because I'm going to be the one that's harder to stop. If my son, even if it's not very fast, my son and I are barreling towards you. If you had to catch one of us, which one would you want to catch? Jack or me? Probably Jack. Your intuition tells you, for several reasons, he's more adorable, he's smaller. Intuition kind of tells you that the less massive thing is going to be easier to stop. But that has nothing to do with how fast they're going. The speeds are the same. This thing, mass has a mass, this is more massive. So more inertia. Harder to stop. But it has nothing to do, but the mass has nothing to do with the speed at which they reach. Is what I'm trying to discover. Leave those there and we'll come back to it. So, the acceleration due to gravity. This here has nothing to do with the mass of the falling object. All objects, regardless of mass, and ignoring air resistance, that's why I put the paper on top of the book. If we're able to ignore air resistance, gravity will affect all objects equally. So it didn't matter which of the 3 balls I tossed into the air, they all kind of went up and went down at roughly the same rate. What would happen if we tossed these things, your understanding, and obviously we've never been there, what if we did the same thing on the moon? What would the difference be? Has anyone ever seen footage from what goes on the moon? The whole thing, it would happen the exact same way, it would just take more time. Yeah. So Ray Reed said they'd fall slower. Another way to say that exact same thing is the process would be the same. It would just take more time. We've been to the moon. There's whether or not you believe that, I'm going to operate under the assumption that that's true. We've been to the moon. There's been footage of people on the moon jumping around. You can see that the moon seems to affect things differently. So then there's got to be less gravity there. If the things would fall slower, if the process would be the same, it would take more time. The moon has to have less gravity, is the only real explanation there. And so then what would be the cause, do you think, of the existence of gravity? What causes gravity to be a thing? If the moon and Earth both have it, but the moon has less of it, what's the biggest difference between the moon and the Earth?
Earth's bigger than the moon.
The Earth is more massive than the moon. And we'll look at it in more detail next chapter, but the acceleration due to gravity has nothing to do with the mass of the falling object. It has I'm going to go back up here and add something here. It has everything to do with the mass of the object creating the gravity. So the Earth is really big relative to the moon. Earth's not actually very big. It creates gravity. You fall towards the center of the Earth. Moon, same thing, small, but you still fall towards the center of the moon. So those two things both have gravity. They also both have mass. You have mass. Do you have gravity? Would it make sense that you would have some sort, you would be a source of gravity? Does that make sense? You have mass just like the Earth does. You just have a lot less of it. We'll look at that more next chapter. So, acceleration due to gravity. All objects fall at the same rate. If we drop a ball from a height, we're going to use we'll talk about the velocity, a sketch of velocity time graph. Does anyone know what the rate of acceleration due to gravity is? Yes, Uli. The Earth has a rate of acceleration of 9.8, roughly, it rounds, meters per second squared. Uli, do you know the value for the moon? The moon has an acceleration due to gravity of 1.67 meters per second squared. And tomorrow we're going to prove that. If we drop a ball from a height, what's going to happen to the velocity? Well, we did this. I had an object. The initial velocity was 0, and we dropped the thing. It went accelerating towards the Earth. The acceleration is constant. So at 0, the time was the velocity. At time 0, the velocity was 0. If Uli's right and the acceleration is negative 9.8 meters per second, 9.8 downwards, or negative 9.8 meters per second squared. Make a chart over here. If I want to chart time and velocity, at time 0, the thing's not moving. After 1 second, if it's accelerating at negative 9.8 meters per second squared, what should the velocity be? Should be negative 9.8 meters per second. After 2 seconds, it's going to be moving how fast? Another 9.8 downwards. So negative, what's 9.8 times 2? What's 9 times 2? Yeah, 18. What's 0.8 times 2? So it's going to be 19.6. After 3 seconds, another negative 9.8. So it's 29.4. So what that means is when gravity causes something to accelerate, like that volleyball or that textbook, after 3 seconds, this thing is now going in excess of 100 kilometers per hour down. 27 meters per second is 100 kilometers per hour. So I didn't pull out a stopwatch when we were dropping those things, but from the 3rd floor of the rotunda, I mean, you could argue it was around 2 seconds, 2 or 3 seconds, between 2 and 3 seconds to fall. If Dwayne had tried to catch that textbook would be moving in the neighborhood of a car on the freeway. It's a good thing Dwayne didn't try and catch the textbook. Hello, Casey. But we can graph that. After 1 second, let's go 10, 20, 30. We'll break that up. After 1 second, we're at negative 9.8. After 2 seconds, we're going to be down here at 19.6. After 3 seconds, we're going to be down here at 29. And you're going to graph, or get a graph that looks like this. A constantly accelerating object downwards. So what's the displacement time, what should the displacement time graph look like for an object like this? I want to tie this back to something you've already seen before. For a graph that looks like this is a straight line, right? So it should have, what kind of equation should a straight line have? What is the general equation for a straight line? Y equals mx plus b. And if the initial velocity was 0 at time 0, then b should be 0. And the relationship here should be that the final velocity is equal to the the slope on a velocity time graph is, and the rise is v, the run is t. V over t is equal to what concept? Sorry? V over t. Change in velocity over change in time is defined to be what? Louder, someone said it. The acceleration. The slope here, remember, the slope on a VT graph is equal to the acceleration. So then, where I had y equals mx, vf is going to be a, and your x variable here is time. And this actually comes from a kinematic equation we've seen before. Vf equals vi plus at. If vi is 0, you're going to get your final velocity is just equal to your acceleration times time. So there's a linear relationship here between velocity, acceleration, and time. What about if I wanted to find displacement? For a constant acceleration, what does a displacement time graph look like? We've been doing this for like a week. Displacement time graph looks like what for an object with constant negative acceleration? It should, yeah. So Kai suggests it should look like this. For those of you who have done Math 11 already this year, what shape does that look like? It looks like a parabola. What's the equation for a parabola? For those of you who have done Math 11 already. Y equals x squared. Well, we've got a kinematic equation for this too. We had a kinematic equation that looked like this. D equals VIT plus 1/2 AT squared. If VI is 0, this is gone. Your y variable is d. Your x variable is t. And you've got an equation that looks like 1/2 negative 9.8 t squared. This graph has the same kind of equation, and it comes from those kinematic equations we've already looked at. So this is, in fact, a parabola based on the mathematical equation it's derived from. There's a deep reason why you study what you study in the pre-calculus stream in math, because so much of it is relevant to the physical world in which we live. So we'll come back to that tomorrow when I'm going to make you guys prove the acceleration due to gravity. So let's graph some more things. A ball is tossed into the air. We're not dropping it now, we're throwing it, like the tennis ball that I threw up into the air. When the thing leaves my hand, Brad said it had a positive velocity. So let's put that on here. Let's assume that somehow I was able to throw the ball upwards at 10 meters per second. What's that going to look like on the graph? Well, it's going to be up here at 10 meters per second. And as soon as the ball left my hand, it started to slow down, which means if the velocity started at 10, I'll use this color, it immediately started to drop. At some point, the velocity hit 0. Where was the ball at that moment in time? Nope. At its peak height. This point right here, the ball was at its, instead of peak, can I say max? It was at its max height. And at that point, the thing started to accelerate back downwards. Eventually, it would have reached negative 10 meters per second. And right here, when the final velocity is equal to the initial velocity, that means at this point, the ball was level with where it was thrown from. Which means its displacement should be 0, which means this area should equal this area, because when you add them together, it should be 0. When you're level with where you were thrown from, your displacement is 0 because you've gone back to where you started. So this guy right here represents the time to the top, and this guy here represents the time to the bottom. So that's what a velocity time graph would look like. Speed time graph looks a little different. Speed is only ever positive. Speed would start at 10. Speed would drop down to 0. But then speed would rise again. Because speed's a scalar. Has nothing to do with direction. Velocity time graph would look like that. For a ball that was thrown upwards, put some time markers on here. 1 second, 2 seconds, 3 seconds. For a ball that was dropped, it was just half the parabola, right? So for a ball that's thrown up into the air, what would you expect the graph to look like, Kai? If I dropped it and got just half of it, you'd expect it, for those of you who've done Math 11, you'd expect it to be a full parabola. And if you think about what happened, if I threw it up there, the ball was, if the VI was equal to 10, it had some initial upwards velocity. By the time you reach the first second, it's going to come to a stop. It's going to turn around, it's going to come back down. So the displacement time graph is going to look like this, when in reality, the ball did not travel this path, the ball just went up and down. It was up, that height comes back down. It's time that causes this whole thing to stretch out. How much time do I have left here? A little bit of time. Let's do a couple examples. Flip over. Some key points to remember. You're going to prove this, but for the time being, I'm going to get you to accept this. The acceleration due to gravity, when we work with the acceleration due to gravity, so acceleration for any falling object, the acceleration is equal to if we're going to get technical, 9.81 meters per second squared. Often, this is not the value we use. Well, 9.81 meters per second down. Generally, this is not the value that gets used. Often, the value that you guys will use is 9.8. We round it, make our life a little bit easier. Meters per second squared. But if you were out in the world and needed to make a point, what value would you probably use to make your mental math a lot easier to use? to do? 10. 9.8 rounds very nicely to 10 meters per second squared. All of these, the acceleration is down. And it doesn't matter if the object is dropped or thrown. For an object that's dropped or thrown, as long as gravity is the only thing acting. This will be the acceleration. There's a couple details that are useful here. For an object that's thrown up, the velocity at its maximum height is 0. We've already said that. And one thing to make really, really clear, the velocity at the bottom is not 0. When you're dealing with a falling object, lots of students, their intuition says, well, the velocity at the bottom is 0. Why does your intuition tell you that the velocity at the bottom is 0 for a falling object? Why might you want to suggest this? What often happens to a falling object at the bottom? Why does it stop? What do you mean it has nowhere to go? It hits something. So it either hits the ground or someone catches it. So what you need to think of here, though, is if I put you at the bottom, if you, Ray, are the reason that that textbook's not going any further, because you are responsible for stopping it, was it going 0 when it got to you? No. You were the reason it becomes 0. So when we talk about the velocity at the bottom of something, what you really need to make clear is, and a way to think about this is, if I was at the bottom, would the velocity be 0 when it reached me, or would I have to make the velocity 0? If the velocity is 0 when it reaches you, you just kind of grab the thing out of the air and there's no problem with this. If you have to be the thing that brings that textbook from 100 kilometers per hour to 0, that's going to be a whole nother set of experiences. The V bottom is not equal to 0. It is moving when it impacts. And is brought to 0. This whole piece right here, the is brought to 0, that's a separate scenario. A wildly unenjoyable scenario if you're the reason that this thing has to be brought to 0. When I was in high school, my buddies and I had a spare study block, and we decided that we would be, hands up if you ever played the game 500 Up? Only one of you's ever played 500 Up? You throw a ball into the air, you shout out a number, it's a point value, and then a bunch of dudes out in the area have to catch the thing. You get that many points if you catch the ball. We did this with a golf ball, and my buddy was driving them out at us. I can assure you, the golf ball does not impact at 0. This is a wildly uncomfortable scenario. I took a golf ball to the thigh. It was awful. Things are moving when they impact you. Okay, let's do a couple. Yeah, do we have time? We do have time. You know what? I'm going to pause here. I'm not going to do any of these examples. You've got one piece of homework for tonight, and here is your piece of homework. Tomorrow, and possibly the next day, we are going to do a lab where you guys are going to verify the acceleration due to gravity is 9.8-ish meters per second squared. Your task before you leave today is to find a partner or a group of 3 to work with. And then you guys, as a group, are going to be tasked with deciding which one of you is going to bring the object that you're going to drop. Because to figure out the acceleration due to gravity, you guys have to start dropping objects.
those. One of you gets one of these.
Bowling ball.
One of those. Did that not give you enough? One of those. 3 of those. Okay, cool. In 2s or 3s. No 4s. 2s or 3s.
I remember when I first.
Here's what you guys are going to do. I'll walk through the lab a little bit here with you now. And then tomorrow, you guys, your only homework for today is to find your group of 2 or 3, and then decide who's going to bring the object you drop, and that person is going to be tasked with finding an object that meets these requirements. So, here's your overview. Galileo. It wasn't Newton, it was Galileo, was the first to experimentally demonstrate that all masses fall towards the Earth with the same constant acceleration. Newton was the guy who said, oh, gravity's a thing, let's figure out gravity. Galileo came along and said, okay, cool. He marched up the Leaning Tower of Pisa and dropped 2 objects off. Regardless of mass, those 2 objects fall towards the Earth with the same constant acceleration. Of course, this constant acceleration assumes that the drag produced by the air is really small or effectively 0. So we made that, Kai was making that argument, air resistance. We call that drag. Assuming you can ignore air resistance, that acceleration is going to be constant. The importance of the role played by the acceleration due to gravity in the historical development of physics cannot be overstated. Wildly important. All physicists at some point in their careers have measured the value of G. I have seen, personally, something like 12 different experiments that all differently verify this. Should you take a physics degree at U of V, there is one lab that you're going to do. So the lab that I'm handing you here is actually part 1 of 3 of a lab that you're going to do at U of V. I taught at U of V for a bunch of years. I did my physics degree at U of V. And this is, I took part 1 of a lab that they do over there, and I beefed it up, and that's what I'm giving to you guys. That lab itself has 3 parts. So there's a bunch of ways to do this. The acceleration due to gravity appears in physics in many disguises. It shows up as an acceleration. It shows up as a force field. We'll talk about that next chapter. As a constant in several important equations, yada, yada, etc. This experiment provides, it says 2 different methods. I took out the second method. It's just one method for measuring the acceleration due to gravity. So your object, the goal of this experiment is to find the acceleration due to gravity. That's it. Here's what you're going to do. You need, as a group, need to decide who's going to bring a mass, an object of your choice, that needs to be between 0.1 and 0.5 kilograms. So between 100 grams and 500 grams. And that is the only piece of homework you're going to have for tonight. Find one of you, per group, needs to find an object between 100 and 500 grams. To put that into perspective, a milliliter of water weighs a gram. So that might be a useful comparison. What you guys are going to do is I'm going to give you tomorrow a piece of equipment called ticker tape. Ticker tape looks like this. It comes off a roll. It's a little bit thinner than this, not much. And it is conductive paper. So we're going to run an electric current through. You're going to take about 2 meters of this stuff. So you're going to get that much ticker tape. And you're going to tape it to your object. I'm going to give you an object tomorrow, and I'll show you in more detail what this looks like. But I'm going to give you an object tomorrow called a ticker timer. So the ticker tape, similar to a tape measure, it's conductive. Don't move. It's conductive on one side. It's metallic paper conductive on one side. You're going to feed it through the ticker timer. You're going to turn the ticker timer on, and you're going to drop the object. What that's going to do, you guys should still have this thing in front of you. What that's going to do is it's going to produce dots on your paper. I'm going to demonstrate this tomorrow. Once you drop the object once, your data has been collected. Now you're going to start to analyze it. You're going to have a bunch of dots on this paper. The beginning dot is where the object was dropped from, and then the dots are going to get further and further apart because as you drop your object, the object's going to be moving faster, so the ticker tape is going to be moving faster, so it's going to pull the tape through the timer quicker. So the dots that timer is making are going to get further and further apart on the tape. Following what I'm saying here? Kind of, sort of. Because those dots are getting further and further apart, we can use those dots to figure out where in space the object was at a particular time. And I'll talk about how we can do that more later. So you're going, tomorrow you're going to do this. Your homework, find your group, decide on an object to bring between 100 and 500 grams. One of you is responsible to do that. I want you to all read through this lab so that there's less that I have to go through with you tomorrow. This lab is going to be a formal lab write-up. The instructions for that are on this page right here. I would like you guys to, in addition to defining your group and your object, read through this tonight to give you an idea of what I'm expecting you to do. There is a bonus section to this lab. The bonus section to the lab is, well, you're going to do a bunch of graphing by hand. If you want the bonus, you're going to, in addition to doing everything by hand, you're going to run through either Desmos, Excel, or Google Sheets in addition to doing it by hand. So you've got two results right there. If you want the bonus, that's how you're going to do it. So your homework, you got it, read through the lab, pick your group, find your object. When the bell goes, you may also go. This is what we're doing tomorrow. Yes, Delaney.
You want to bring the look like?
Between 100 and 500 grams.
Between 100
That, yes, that is just over 1 pound. Yes. Your object could be just over a pound. Yes. Yes. Okay. When the bell goes, you may also go.
Yeah, in case Gil shows up, I'm going to bring some too. Oh, any food is funny.
Okay.
No. That's like 10 grams. Look, you know, like an average like a chicken breast.
Everything.
Yeah, it's probably something like that. Maybe a little heavier. Heavier like that. That's like right in between.
And the data. So
The average.
this line
You just see the modified space every time. It's like
this is more mass. I look over this. Is relative to that.
I was holding it together, so I saw you, and I was like,
This one would be
that's
right here. That's here to here, here to here. This would be three triangles. This triangle, do this triangle, you do this triangle,
and that's like an apple.
well, this is going to be half base times height. This is going to be half base times height. This one's going to be half base times height. That is
She doesn't even snap.
yeah, where you did the shape from is incorrect. And you didn't make it 0.06 yet. No, it wants the both of these want the total displacement because you go all the way through. So even on both of them, you didn't include that last piece there.
It's your birthday? Happy birthday. My birthday is so fun.
This guy would go here to here,
Right?
here, there, here. Yeah, that's right.
Sure.
Yeah, absolutely. Yeah. Are you fan? Aren't you on it today? And tomorrow. Mr. McDonald did not mention that when I was hanging out with him this morning. All right.
Okay. Between 100 and 500 grams. So as Dwayne said, that is like a quarter pound to a pound if you're doing things in pounds. 400, what is it, 457? 457 or 474 grams is a pound? I think it's 474.
Just like 220 grams.
It's 2.2 pounds in a kilogram.
Oh, wait, yeah.
Go the other way. I think it's 474 grams in a pound. Okay. Okay, have a great day, guys. Yeah, man.
So you said that falling object's mass is irrelevant to how fast it falls, right?
Correct.
So how is that true when we're on falling object?
What do you mean? How are we on? What do you mean we're on a falling object?
Earth is down can only be described as the direction that gravity is pulling you.
Yeah.
Within the universe, and Earth is being pulled towards the sun.
Is it though?
Is it? Is
it exclusively being pulled towards the sun?
Isn't it? Isn't that the only reason that it doesn't leave the solar system?
Would you? So here's a question for you before I answer that. Right. For an object in orbit, would you consider that object like an astronaut on the space station? Would you consider them to be falling?
Well, yeah.
Okay, then yes, we're talking about the same thing.
So then, if Earth is falling, Earth's mass.
So Earth, hold on. So Earth is falling towards the sun.
So
what's the sun doing? Where is the sun?
Gravity isn't effective between galaxies, right? They're not.
Oh, it absolutely is.
They're not living each other's gravitational
Oh, they absolutely are. That's why the Milky Way and Andromeda are doing this. But before we even leave the galaxy, so our Earth is doing this around the sun, but the sun is doing this around the center of the galaxy. We've got a supermassive black hole, or a group of them at the center of the Milky Way, and the galaxy itself is spinning, and the galaxy itself is moving through the universe. So it's actually approaching Andromeda, but the fabric of the universe itself is expanding. So it's not just simple simple enough as to say the Earth is falling towards the sun, because it's way more complicated than that.
Okay. So it's not as simple as just moving in the direction of gravity, therefore falling.
For an object to be in orbit, you need to be moving in the direction of gravity with some tangential velocity.
Okay. So since the Earth is moving towards the sun, but isn't moving towards it with velocity, since its distance from the sun is staying the same, or relatively the same.
Not quite that cut and dry. Okay. I need a string. You want to talk about this? I need string. Get a battery for this before I forget. Bring a battery from home for that. Okay, so I have this.
I got a rugby game today. I'm gonna make you class.
Okay, the video.
What?
Take a look at the video.
Okay. Can we get the text and the balancing?
The balancing quiz. You betcha. Oh, hey, Michael, you did the balance. Sorry, Memphis.
You did the balancing quiz, right?
Yeah.
Okay. And see you later. Here you guys go. Okay, so here's a way to demonstrate that. What's that? A writing utensil? You don't have your own?
Oh, it's not working. The ink's out.
Here you go.
Yo, I can't show up for the provincial now because I have someone.
In May? On the 2nd? Okay.
I can't.
You sure it's the same day?
Yeah, exactly. It's the Friday, right?
Yeah.
Yeah, so I can't.
Okay. Thank you for letting me know. Okay, so here's how we're going to mimic this. If I have this, hopefully it doesn't come untouched. Like the reason that this thing's moving in a circle is because I'm pulling in on it with the tape. But it also has so like every point along the circle, the tape is trying to go straight. So when it's straight out, at this point, if I let go of the string, the thing would go straight up. At that point, if I let go of the string, it would keep going down. So the Earth is objects in orbit are moving
at their own straight velocity, but
tangent velocity, and gravity's pulling them in. So really, like, they are falling, but they're constantly missing. So if you don't like that feeling of falling on a roller coaster, that's the same feeling astronauts experience the entire time that they're there. Because you're right, they're constantly falling. They're just missing the Earth the entire time.
and that's why the moon does that shape rather than this.
So the moon's doing the same thing. It's an orbit. It happens to be elliptical, not circular. We approximate it as a circle. It's because it's easier. But when you do actual orbital mechanics, you'll see for reasons that it's elliptical. So it's not even straight elliptical. Yeah, it is. It's elliptical. Because
It's kind of being squished up.
no, it's more complicated than that even. Because we are moving, the Earth is impacted by the sun's gravity, but the sun is actually also impacted by our gravity. Because every force has an equal, for every action there's an equal and opposite reaction. Earth is being pulled on by the sun's pulling on the Earth. Sorry, sun's pulling on the Earth is also pulling on the sun in response. So we don't orbit the center of the sun. We and the sun actually orbit a point in space inside the sun, but not at the center of the sun. So the sun has this wobble. And it's not just us that's doing this, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Everything that's orbiting the sun is orbiting at a different space between the center of the sun and the center of that object. So you get this kind of wobble that happens, which is part of the reason that those orbits are elliptical, not spherical. Or it's circular. They're elliptical, not circular. And all of these massive objects, so we have a gravitational effect on the moon. The moon also has a gravitational effect on us. Jupiter has a massive gravitational effect on everything else in the solar system. It's the second most massive object to the sun.
It affects us.
That's everything. Jupiter is the reason we haven't been hit by asteroids in our human existence. Big enough to wipe us out. Because it functions out there as a big sweeper. Its gravity just kind of pulls everything towards it.
Clearing the neighborhood.
Yes, the idea of clearing the neighborhood. That's what Jupiter's done for our solar system. So when you go back to say that we're just on a falling object, falling, I guess that definition is all about moving towards the center of whatever object is impacting you most gravitationally. So yeah, we're falling towards the center of the Earth. The Earth is falling towards the center of the sun. The sun is falling towards the center of the Milky Way. The Milky Way is falling towards Andromeda, or vice versa. They're falling towards each other in a very loose sense. Not in the way that we would expect falling. toss you out the window. That experience of falling is different intuitively to what a lot of people understand what you're describing as moving towards a source of gravity.
And that goes back to my original question, which is, if it is two bodies of gravity affecting each other, and mass is the effector, sorry, not mass is the effector, gravity is affected by the level of mass of something has more mass of something than gravity.
Yep.
So why is mass irrelevant to gravitational force? Because if one thing is pulling on another, one thing is pulling on this thing's pulling on this thing. If one of those forces is stronger, then the total attraction force should be stronger as well, shouldn't it?
Next chapter, I'm going to show you this equation. The force of gravity is equal to the mass of an object times the acceleration due to gravity. This is what I've been arguing today is the same for all objects. The book, the volleyball we dropped off the rotunda, the textbook we dropped off the rotunda, the paper on top of the book that we dropped in the classroom here. This value is what I was arguing today is the same. This is not.
Right.
The force of gravity is not equal on all objects.
So how hard is
This, hold on, this we call weight.
Right.
So different masses have different weights. So the force of gravity is different on all these objects. But the acceleration due to gravity on all these objects is the same.
And the same speed, but the mass impacts just how hard it hits for something. Like you drop the book off the rotunda, how hard it hits the floor is different from how fast it's moving because the mass.
Yeah, the forces on those objects is going to be different.
Right.
And so the force that you're going to have to exert to catch those objects, that's why catching them is going to be different.
Right.
They're both moving at 100 kilometers per hour, but I'd way rather catch the volleyball than that biology textbook I got.
Okay.
Because of that value, not because of this value. And this is what's dependent on the mass of the object.
Okay.
I'm also going to show you that this is dependent on some universal gravitation. Hey, Raina's here. Universal gravitational constant times the mass of the gravity creator divided by how far you are away from that gravity creator squared.
That does make sense.
So the further you are away, the smaller your acceleration due to gravity is.
And that's why when you're on the moon, you would fall towards the moon even though you're in Earth's gravitational field because you're too far away from Earth.
Yeah, you're in
to
both
avoid-
fields.
But the moons would be greater when you're on.
The impact of the moon, yes. And there's actually a point in space, just bring it right down, mark it right away. There's a point in space between the Earth and the moon where you would be, it's closer to the moon because the moon has less gravitational pull. But there's a point in space between the two where you are impacted equally by the Earth and the moon and you're just going to float there between the two. Hold on, don't leave yet. Okay, come over here, Lexi. Largely well done. When you were counting oxygen, when you were counting, so you said that this was the coefficient here on this, because you said that there's this times this is also this. But that's not good. Yeah. These two are good. That one's good. So easy to fix. Go back and take a look at the play with that one a little more. Not now. But this shows me that you know shit. So, no, I'm gonna die. Oh, wait a second. Yes, you're going to put them in your folders. Yes, I'm going to put it in the box and I'm going to put it in your folder. Have fun.
Yeah.
Manage the heck out of those boys. Are you in C or D? I can't remember.
I'm in C.
You.
See ya.
See you later. Did that answer your questions?
It is.
More complicated of an answer than perhaps you were expecting. Okay.
That one term, force of gravity over its.
Sorry?
It was just that one term of force of gravity over its.
Yes. Fundamentally different, but they're very much related. Raina, how are you?
I'm good.
Hold on, don't say anything.